Welcome back to our machine design series. Today we are discussing spring materials. So the types of materials we select for springs that we want to manufacture. They can either be made by hot or cold working processes depending on the size of the material, the spring index, and the properties that you desire in your spring. In general, the ideal spring material would have high strength, so high ultimate strength. This helps it resist both static and fatigue failure. High yield strength. This helps it avoid excessive deformation during service. And a low modulus of elasticity. Because remember, our goal with a spring is to have a lot of deformation, to absorb a lot of energy that way. And so we want to have a low modulus of elasticity so that we can get lots of deformation. There are many different spring materials. Large variety are available to you as a designer, including plain carbon steels, alloy steels, corrosion-resistant steels. There's non-ferrous materials. And so you can take a look at table 10-3 in Shigley for a description of some common types of spring materials. There's music wire, which is the toughest, most widely used spring material for small springs. It also talks about oil-tempered wire, hard-drawn wire being probably the cheapest spring steel. In any case, you can take a look at all of those in Table 10-3 in your textbook. And then one thing that we can use to compare all these different spring materials is their tensile strength. Tensile strength varies widely depending on the diameter of the wire size, and so much so that actually we need to specify the wire diameter before we can even estimate the tensile strength of the material. So as the wire diameter gets smaller and smaller, the tensile strength goes up until the point where it actually approaches the strength of the atomic bonds holding the material together. And so we can write an equation that relates the tensile strength of the spring material to the wire diameter. So the tensile strength, which I'm going to write as SUT, depends on the wire size, which we're going to continue to use a lowercase d for that. And our equation that relates those two variables is SUT equals capital A divided by wire size to the m power, where A and m are material constants, meaning that they vary depending on your material. which you can find in table 10-4. For some common spring material types. The other strengths that we would like to know are the yield strength and the torsional yield strength, because remember when we talked about the estimating stresses in our spring material, let's find where that equation is. Our stress in the spring is largely a shear stress, and so we need a torsional yield strength to compare this torsional yield stress. And those values can be found in another table. So yield strength which we write as SY, and torsional yield strength is S sub SY, can be found in table 10-5. So a lot of the work of these problems is knowing how to use the equations is the key part, and knowing which table to go to find the constants and the strengths that you need is the other big component of problems in this chapter. So with that, let's work through an example, start to finish, that will incorporate everything we've learned so far about springs. Okay, so here's our example problem. We have lots of different parts to go through, but we're gonna take them one by one and get through this whole problem with ease, using all that we've learned so far about springs. So first of all, let's dissect this problem statement. We have a helical compression spring that is made of number 16 music wire. So we haven't encountered this before, but this number 16, this is key to finding out the actual wire diameter. There is another table in your textbook. This is going to be found in table A-28, and there you will find gauge numbers along with their respective diameters of the wire. Okay, and then we're also told that the outside coil diameter, remember this is the outside diameter, so we're going to need to find the mean diameter at some point. But we're given this outside diameter as 11 millimeters. We're told that the ends are squared, so remember that just means that the ends have been sort of flattened, but not ground. So the ends have just been deformed so that we have the last coil flat against the surface. And there are 12.5 total turns. Okay, so let's move some of this stuff out of the way and get started with part A. All right, so part A asks us to estimate the torsional yield strength of the wire. Now remember that we just talked about this equation, which we're going to need to use, this SUT, because we're looking for torsional yield strength, and that is going to depend on the tensile strength of our wire. So we're going to start with this equation. Let me just copy it. Okay, we know we need that. From table A-28, I can find that gauge 16 wire is a diameter of 0.94 millimeters. And then from table 10-4, I can find the A and M material constants for music wire, and they are A equals 2,211 megapascals times millimeters to the M power, and M is 0.145. All right, so with that, we have everything we need to solve for this ultimate tensile strength. So 2,211 megapascals times millimeters to the M power, where M is 0.145. This is just to show you how the units end up canceling. And then we have 0.94 millimeters to the 0.145 power. So you can see that the millimeters to the 0.145 power are on both the top and the bottom, and so those units are going to cancel, and we're going to be left with megapascals, which is perfect because that is the units of strength. So if I do this calculation, 2,211 divided by 0.94 to the 0.145 power, I get 2,231 megapascals. That's our ultimate tensile strength. Now we need to go to another table. So table 10-6 gives us an estimate of the percent of tensile strength that our maximum allowable torsional stress is going to be. So for music wire, which is the top row of this column, and before the set is removed, so we're not told that this spring material is processed and then heat treated to remove the set, or set by compressing it to its solid length. And so that means that this is a material before set is removed. And the table tells us that we have 45% of the ultimate tensile strength is equal to the torsional yield strength. And so all we need to do is plug into this the ultimate tensile strength that we just found. So 0.45 times our previous answer gives me 1,004. For our torsional yield strength. All right, that's part A. Easy enough. right? It's all just looking stuff up in tables, knowing where to go. Okay, so then part B, we need to estimate the static load corresponding to the yield strength. Okay, so now we're going to need to find the mean coil diameter. So our mean coil diameter is equal to our outer diameter minus the wire diameter. We talked about this in the first video when we were just introducing, or maybe the second video when we were talking about the specifics of helical compression springs. So this is going to be 11 millimeters minus 0.94 millimeters. 11 minus 0.94 is 10.06 millimeters. Okay, and so now we can find our spring index, which this is from the first video. So our mean coil diameter divided by the wire diameter. So 10.06 divided by 0.94 millimeters is 10.7. Okay, now we can find our torsional yield stress, so our tau max. Let me move some of this stuff out of the way. Okay, remember that our maximum shear stress, let's just go up and find the equation again. It was this one. Okay, and our question asks us to find the static load corresponding to the yield strength. So I have a torsional yield stress, which I can use in place of this stress to find the static load F that corresponds to that yield strength. So we're looking for the load that is going to cause our stress to be equal to yield. Okay, so I have everything I need in this equation except for Kb, our Bergstrasser factor, which we can calculate from 4c plus 2 over 4c minus 3. So that's 4 times 10.7 plus 2 over 4 times 10.7 minus 3. So 4 times 10.7. Okay, so I get about 1.126. All right, now I have everything I need to plug in to this equation. And first I'm gonna actually rearrange it a little bit because I wanna solve for F, not for tau. And I'm gonna replace tau with my torsional yield stress. So I'm gonna wind up with F equals pi d cubed times my torsional yield stress divided by 8 times the Bergstrasser factor times the mean coil diameter. This is just rearranging the original equation. And now let's plug in what we've got. So I've got pi times 0.94 millimeters cubed times my torsional yield stress, which was 1,004 megapascals, divided by 8 times 1.126 times the mean coil diameter of 10.06 millimeters. Don't forget to change that from 11. It's not 11 millimeters, it's 10.06. Okay, so let's calculate this. Pi times 0.94 cubed times 1,004 divided by 8 divided by 1.126 divided by 10.06. I get 28.9 newtons, 0.91 newtons. Okay, and remember that our units here, the reason that I was able to leave the megapascals and millimeters is because 1 megapascal is equal to a Newton per millimeter squared, right? Because millimeter or 1,000 millimeters makes up 1 meter, so this is equal to 10 to the 6 newtons per meter squared, or 10 to the 6 pascals. If that's confusing to you, you can always convert your megapascals back into pascals and your millimeters into meters. You'll get the exact same answer, but this just saves you one step, which could be the difference in making a mistake or not. So megapascals and millimeters and newtons, those are sort of what we'd call consistent units. All right, so we found our static load. Let's box it. That's our static load corresponding to the yield strength. Next, the question asks us to estimate the scale of the spring. What does it mean by that? It just means the spring rate, spring constant. So for this problem, we're going to need to use table 10-1 to find the number of active coils. So I know that my number of total coils was 12.5. Let's go up to that table. We can see how to use it. So my spring ends were just squared, not ground. So that would correspond to this second to last column here. And I want to find the number of active coils from the number of total coils, so I need to use this equation here. So number of total coils equals number of active coils plus 2. Let's go put that down here where we're working. Okay, so from this table, we found this equation. And again, my number of total coils is 12.5. So that's equal to my number of active coils plus 2. And therefore, my number of active coils is 10.5. Okay. Next, we go to table 10-5, and there we find the shear modulus of the spring. So in table 10-5, for a music wire for a diameter of 0.94 millimeters, that's going to be second row of that table, we find that our shear modulus is 81.7 gigapascals. All right, so now we have everything we need to be able to use our equation for the spring rate which is this one here. Okay, so let's plug it all in. We've got 0.94 millimeters to the fourth power. We've got 81.7 gigapascals. I want to convert this into megapascals so that it will be consistent units with the millimeters. So I'm going to multiply this by 1,000 to make it megapascals. And then divide it by 8 times our mean coil diameter, 10.06 millimeters. That's one of the most common mistakes I see. Don't make it. 11 millimeters is 10.06. And the number of active coils is 10.5, which we just found. Okay, so let's plug all of that into our calculator. 0.94 to the fourth power times 81.7 times 1,000 divided by 8 divided by 10.06 to the third power and divided by 10.5. I get 0.746. Now, what units does this have? So I have megapascals on the top, and I have these millimeters to the fourth power and then millimeters to the third power here. So those are going to mostly cancel, and my units end up being megapascals times millimeters. Well, remember that this is the same thing as, or a megapascal is the same thing as a Newton per millimeter squared. So I multiply that by a millimeter. I can cancel one of those millimeters on the bottom, and my units are newtons per millimeter. And we like to use these units of newtons per millimeter because it is a force unit divided by a distance unit. It's the way that Hooke's law is set up, right? A force and a distance are related by this spring constant. And so having a force divided by a distance for our units is going to be the way that this constant makes the most sense. So let me just rewrite it in the units that we like. 0.746 newtons per millimeter. If you left it as megapascals times millimeters, that's not wrong. It's just maybe confusing for the person who is reading your final answer. If you are working in industry and you give your boss this number of megapascals times millimeters, they might not know what that means if they're more familiar with seeing spring constants in units of newtons per meter, newtons per millimeter, or some force unit per some distance unit. So having correct units is helpful. All right. Part D. We want to estimate the deflection that would be caused by the load that we found in part B. So the load that we found in part B was 28.91 newtons. Okay, and we were just talking about Hooke's law, so let's use it. Hooke's law, remember, is F equals K Y. So our spring constant times our deflection. We have a force, we have a spring constant. We can solve this for the deflection. So Y is equal to 28.91 newtons divided by 0.746 newtons per millimeter. Now you can see why changing those units was so useful. We can directly see with Hooke's law that these Newton units cancel. This millimeter unit comes up to the top, and we are left with units of millimeters. So 28.91 divided by 0.746 is 38.83 millimeters. Okay, it's as easy as that for part D. Next, part E. Estimate the solid length of the spring. For this one, we can go back to table 10-1 to find an equation for this. So let's go up here. Here it is. We want the solid length of the spring, and we still have our squared ends. So here's our equation. The solid length of the spring is equal to wire diameter times the number of total coils plus 1. So let's put this down here where we're working. Okay. I have everything I need to plug into this equation and find the solid length. So let's do it. 0.94 millimeters for the wire diameter. I have 12.5 total coils. That was given in the problem statement. And so my solid length is 0.94 times 13.5. 12.69 millimeters. As easy as that. All right, part F. What length should the spring be to ensure that when it is compressed solid and then released, there will be no permanent change in the free length? Okay, so essentially what this question is asking is for us to avoid the yield strength. And we've already sort of figured out what that force is that causes us to just reach the yield point, right? That's what we did up here in part B, is find the static load corresponding to yield. And then we took that load and we found the corresponding solid length of the spring. And we found in part D the deflection caused by this load. So all we need to do is make sure that the free length of our spring is greater than this deflection that would be caused by the load plus the solid length of the spring. So our free length should be equal to deflection plus the solid length, which was 38.83 plus 12.69 millimeters. Okay, so our free length, 38.83 plus 12.69. It's 51.52 millimeters. Okay, so as long as the free length of our spring is 51.52 millimeters or less, when we apply this load, we will reach the solid length of the spring before we reach the yield strength of the material, meaning that there will be no permanent change in the free length. All right, almost done. 2 more parts. So given the length found in part F, is buckling a possibility? So remember that when we were discussing buckling, we found this equation for steels. Well, we found an equation for the free length to have absolute stability. We said that it must be less than pi times d divided by alpha times 2 times E minus G divided by 2 times G plus E to the 1/2 power. And in this problem, we've found our shear modulus already. We said that G is equal to 81.7. In that same table where we found this, which is table 10-5, we can also find the Young's modulus right next to the shear modulus, and it is 200. These are both in units of gigapascals. All right, so that's E and G. We have our mean coil diameter worked out already. The only thing we don't have so far is alpha. If we take a look at table 10-2 for the end condition constants, we will find that a spring supported between flat parallel plates, so a spring with fixed ends, has a constant of 0.5 for alpha. Okay, so we use this constant of 0.5 because it's the lowest possible constant, which is going to give us the greatest possible length that we need to be less than. Okay, so now let's plug it all in. Our free length needs to be less than pi times our mean coil diameter, which was, where is it, 10.06 millimeters. Divided by 0.5. Okay, and then we plug in our moduli, so 200 minus 81.7, and 2 times 81.7 plus 200 on the bottom to the 1/2 power. Okay, so let's plug all this in. 2 times 200 minus 81.7 divided by 2 times 81.7 plus 200, and all of that square rooted. Okay, and then times pi, okay, times 10.06 divided by 0.5. All right, so my free length needs to be less than almost exactly 51 millimeters. Okay, so my free length is just above that. So that means that buckling is a possibility, although I am right on the cusp of being under this. So if we carefully control the forming of the ends so that we make our alpha constant here go down a little bit more, then we will have a free length upper limit that's a little bit larger, then we'll be underneath that value. The other thing that we can do is we can place an inside rod into the middle of our spring. So this is something we didn't talk about much when we were discussing buckling. But one easy precaution to take to help avoid buckling is to take our spring and simply place a rod through the center of it so that if the spring does want to buckle, it's going to actually contact this inside rod. Another thing that you can do that has essentially the same effect is you can take your spring and you can place it in a hole, so that the same thing happens. If the spring wants to buckle, it'll start contacting the sides of the hole before it buckles too far. So if those are options, that's a good way to help prevent buckling. And this is actually what you have inside your ballpoint pen, right? It would be this rod. Actually, you have both, because the spring inside your ballpoint pen sits on a rod, which is the ink container, and then all of that goes inside a hole, which is the housing for your ballpoint pen, where the grip is located. So your ballpoint pen actually does both of these. All right. Okay, so buckling is a possibility. And we may want to think about some precautions to help avoid that. Next, we have part H, last part of this problem. We want to find the pitch of the body coil. So again, we can look to table 10-1 to find this. Coming up here, table 10-1. Okay, and now I'm looking for the pitch. So the pitch is equal to free length minus 3 times the wire diameter divided by the number of active coils. Let me cut that. Okay, and I've already got everything I need to plug in here. So my free length was 51.52 minus 3 times the wire diameter, which was 0.94 millimeters, and then divided by number of active coils, so that was 10.5. So 51.52 minus 3 times 0.94, and then divided by 10.5. My pitch is 4.64 millimeters. And remember, pitch is the axial distance between coils. So roughly what I've drawn there. All right, so that is a full example problem using everything we've learned, or pretty much everything we've learned about springs so far. This is very similar to a problem that I might use on our next in-class quiz, so I encourage you to try this one out, make sure that you understand it. Let me know if you have any questions. And otherwise, thank you for watching and hope to see you in the next one.